most fun. Do it. Like this will roll out and go.
Just getting by.
We're all just making all the same back and grow the strip.
Oh, for pity's sake.
Right there with you.
What is your problem?
Yeah. He's about a 48-hour nap right now.
This is frozen.
Yeah. There we go.
Okay, what's wrong here?
Don't come at me. Don't come at me first.
Sorry, you're right.
Okay. Let's go ahead and get started. So for those of you who will come to lab tomorrow, we're going to do a reaction time lab. We'll probably break you into two groups. Amanda will run the group on one end of the room. I'll run the group on the other end of the room. You'll have headphones on. You'll hear a little sound, and then you'll have a hand device you'll be asked to essentially press whenever you hear the sound. You'll go through it where the sound will be random, and you'll have to press it. Then there'll be sounds that occur every 5 seconds, and you have to try and anticipate. You'll be much faster, of course, when doing it that way. You'll do it with the dominant hand, the non-dominant hand. We'll compare differences between the dominant hand and non-dominant hand, see if there's a reaction difference. This is always interesting with people who play sports that require reactions like baseball and softball, stuff like that, because they tend to be very good at reactions, whereas those who do things that don't require reactions like bowling or golf aren't quite as fast. And that's just honing essentially that when you see a ball coming at you at 90 miles an hour, you have to react fast or you're going to strike out. Yeah, or soccer, if the ball's coming at you, I don't know how fast the ball travels in soccer, probably pretty fast sometimes. Either that or you have to get your head out of the way or else a foot's going to, right, greet you right in the teeth. So those reactions have to be fast too. To get thee up and get thee out of the way. So that'll be lab tomorrow. It'll be pretty fun, I think, to see the difference between dominant and non-dominant arms. I always get very interested in the difference between people who are right-handed and left-handed, because all our research of right and left-handed people say the people who are right-handed, the right hand is much more dominant than the left hand, whereas people who are left-handed, the two hands are actually more equal than a right-handed people. So it'll be interesting to test. How many are left-handed? Just, only two lefties? Oh, crumbs. Okay, so we'll be interesting to test the lefties to see how different the lefties are between the two hands, as opposed to people who are right-handed. That will be quite interesting. Very good. So we are going to finish the energy production part and then move on to transport. And we have a person who just learned today they have to be quarantined. So poor Luke, this is for Luke. Hopefully he'll get on pretty soon. So, all right, let's have a word of prayer, then let's begin. Lord, thank you for this day. We thank you that it was a tad warmer yesterday, and now we're looking at a pretty cold week again. So we pray for our athletes who have to travel and some of whom have to play in cold like this. Please help us to stay healthy. Please help us to live smartly and avoid sickness. Thank you for every student here. We pray for lab tomorrow and on Thursday that you would go before us and let us learn what we need to learn. And now go before us and help us to learn hear what we need to learn in Jesus' name. Amen. All right. So we saw last time that glycolysis, which remember occurs in the cytosol, can occur backwards in order to make sugar. The main organ where this occurs is in the liver. This is regulated by hormones. The main hormone is glucagon that will encourage this process called gluconeogenesis. So glucagon will encourage gluconeogenesis, insulin will discourage gluconeogenesis. So if, for example, let's say Bethany were to make a huge pan of brownies for the class and distribute them throughout the class, we'd all have brownies, our insulin would kick in and our gluconeogenesis, if it's going on in your liver, would stop, and it would stop pretty quickly. Because of the sugar, that would induce the insulin made by the beta cells of the pancreas. If, however, all of you decided to go on a fast to protest the lousy food in the DC, and so you were here without having eaten anything all day. Now, not all of you have meal plans, I realize that, but just pretend you did. Then you would, at this point in time, your gluconeogenesis would be really revved up because your last meal, whenever it was, would have been, say, the day before. Now your glucagon levels are high, but your brain needs glucose in order to work. That glucose is going to come either from stored glycogen. What happens if you use all that up? Well, then you're going to go to carbon skeletons made from amino acids. Those carbon skeletons made from the amino acids are taken from skeletal muscle. That's a result of glucocorticoids made by the adrenal cortex. And then the amino acids are deaminated in the liver. The alpha amino acids are then converted into glucose via gluconeogenesis. That's due to high levels of glucagon. This, in fact, is one of the reasons why breakfast is one of the most important meals of the day. Did mom ever tell you that? Yes. Turns out mom was right. You know why? Because glucocorticoid levels spike when you wake up. That's why morning is the time when you have the most heart attacks, because of spiking glucocorticoid levels. At that time, you've been fasting all through the night. Your brain needs glucose. If you don't eat breakfast, what's going to happen? Your cortisol is going to cause you to lose muscle. If you eat breakfast, now that increase in blood glucose is going to come from the food you eat, not from skeletal muscle. So if you want to build and keep skeletal muscle, eat breakfast. Eat breakfast. See, mom was right. We're going to see a lot of instances in this class where mom was actually right. So besides this, the other lesson for the day is listen to your mother. Now, how do you go about making constituents? We told you how you break them down for energy. Sugars are broken down by glycolysis, and then they're broken down to pyruvate. Pyruvate goes into the mitochondrion. It gets converted into 2 carbon entities, acetate. Those are then carried by coenzyme A into the mitochondrion. They're broken down to carbon dioxide. The excessive reducing equivalents are sent to the electron transport chain. Lipids are broken down to glycerol and fatty acids. Fatty acids are sent to the mitochondrion, where they're broken down by beta oxidation into 2 carbon elements that are converted to acetyl coenzyme A. Those go through the Krebs cycle, same song, second verse. Glycerol goes straight into glycolysis. Very easy to take glycolysis, turn it into glyceraldehyde 3-phosphate, which directly enters glycolysis. Amino acids will enter either glycolysis or the Krebs cycle. Most of them enter the Krebs cycle, a few of them enter glycolysis. They therefore take many of the same routes as sugars. How do you make these things? Polysaccharides, if you want to make polysaccharides, you're going to first make monosaccharides. So remember, monosaccharides are made via gluconeogenesis. You make it by taking glycolysis, running it in reverse, or you get monosaccharides straight from your diet. Then you're going to link those monosaccharides together one at a time to make a polysaccharide. Now, sugars just can't link together. That is a very energy demanding reaction. You need to activate the sugars. So you're going to take ATP and use it to make uridine triphosphate, UTP. UTP will react with the sugar to make uridine diphosphate bound to the sugar. That's going to be the carrier. That activates the sugar. And now UDP, sugar, will be able to participate in the polymerization reaction. So you're going to have to burn an ATP to be able to activate the sugar. So virtually all of your enzymes involved in making polymers will bind UDP-bound sugars. That's how essentially you make polysaccharides. Lipids are made from acetyl coenzyme A. You take acetyl coenzyme A. There is an enzyme called acetyl coenzyme A carboxylase that makes an intermediate called malonyl coenzyme A. This is the material for the synthesis of fatty acids. You typically make C16 fatty acids, palmitate. Then there are separate machineries in your cell for either putting in double bonds. They're called desaturases. Desaturases. Very interesting set of enzymes. Those are found in the smooth ER. Also in the smooth ER are enzymes called elongases. Elongases. Those will add carbons to the fatty acid, and you'll get longer chain fatty acids than just C16. You get C18 stearate, or C20s, or C22s, or C24s, or something like that way. Making fatty acids is a very energy demanding process. It takes a lot of ATP, takes a lot of reductant too. Now, when you make things, you will not use NAD, you will use NADP. You'll use a reduced version of NADP, use NADPH. So NAD tends to be used for catabolic reactions, tends to be used for things that break things down, catabolic reactions. NADPH is used for anabolic reactions where you're making things. So if you have a reaction that is making things and you need to reduce it, 99 times out of 100, you will use NADPH. If you are breaking something down and you need to accept electrons from something, 999 times out of 1,000, it'll be NAD and it'll be reduced to NADH. To make triglycerides, you just take fatty acids and you esterify them to a glycerol. You use enzymes called acyl synthases. Acyl synthases. There's several different types of acyl synthases that can attach fatty acids to glycerol. That makes triglycerides. Triglycerides, remember, they're used for storage. They're not used for structural entities, they're used for storage. And you make them from acetyl coenzyme A. Incidentally, cholesterol is also made from acetyl coenzyme A. Cholesterol essentially is a polymer of acetyl coenzyme A that is then cyclized. And that's essentially how you make it. So you can make cholesterol from dietary fat. Since you make coenzyme A from dietary sugar, can you make cholesterol from dietary sugar? Yes, you can. In fact, high sugar diets actually can jack up your cholesterol more than high fat diets can. That's why people who cut fat out of their diet end up replacing it with carbohydrates, and that actually makes their situation worse. So be careful of low-fat diets. They're often worse for you than the fat you would eat normally. How many of you in here have had Mitch and Beth's nutrition class? They probably mentioned some of that. And I know Mitch in particular is pretty merciless when it comes to fad diets. He's got very little patience for fad diets. So he's a good resource for good nutrition, especially if you're an athlete, you're trying to build muscle. Glycerol is made from Krebs cycle intermediates. Sorry, glycolytic intermediates. So you take glycerol and you esterified fats, say fatty acids to it. That's how you make triglycerides. If you're trying to make phospholipids, you do the same thing, except you only put 2 fatty acids with the glycerol, and then you add phosphate and a head group, and you have a phospholipid. Phospholipid synthesis, as we said, starts in the smoothie R and then ends in the Golgi apparatus. Amino acids, we can only make some amino acids. Those are the non-essential amino acids that we can make. The rest we have to get from our diet. Those are the essential amino acids. All the amino acids that we can make come from precursors that are the products of glucose oxidation, essentially. And so things like glucose 6-phosphate, that gets used to make histidine, and 3-phosphoglycerate, that comes from glycolysis, that's used to make serine. Serine then is used to make cysteine, and is used to make amino acid glycine, and things like that. And then several tricarboxylic acid cycle precursors, intermediates. Krebs cycle intermediates are used to make other amino acids. So glutamate, glutamine, arginine, proline, they're made from alpha-ketoglutarate. Aspartate is made from oxaloacetate, and then asparagine is made from oxaloacetate as well. Virtually all the others you are going to need to get those from your diet. And this is just some of the reactions that are used to make some of these other amino acids. The amino acid alanine is made from pyruvate very easily. It's one step. Those are the ones that you can make. The others you need to get from your diet. And here's a nice little picture, once again, shamelessly stolen from the book. That shows you where some of these amino acids come from. There it goes. So, yeah. And if you don't see it on here, you may need to get it from your diet. Yeah, aspartate, as we said, comes from oxaloacetate, and then asparagine is made from aspartate. Now, if you are eating protein, the example we used last time about Kelsey getting a nice sirloin from Cattleman's, all those amino acids, if you're going to use the carbon skeletons, you need to take off the amino group. That amino group is going to produce ammonium. Now, you don't want ammonium flitting around your body at very high concentrations. Ammonium is a metabolic poison. So instead, your liver is going to take the ammonium and convert it into urea. This pathway is also a cyclic pathway, and it was actually discovered also by Hans Krebs, the same guy who discovered the Krebs cycle. This is called the urea cycle. And the urea cycle occurs predominantly in the liver. So ammonium looks like that, and urea looks like this. That's urea. So you can see that's where one of the ammonia molecules went. Here's where the other one went. Where do you think this comes from? You breathe out carbon dioxide, right? That comes from carbon dioxide. So carbon dioxide, water, and ammonium will be used to make urea. Urea, fortunately, is relatively innocuous. And it's used actually by the kidney to make essentially certain types of solute concentrations that your kidney will use for filtration purposes. At very high concentrations, urea will denature proteins. Concentrations will never get that high inside your body. Liver disease can cause a condition called ammonification of tissues. Ammonification is not only dangerous to cells, it's also dangerous to the brain because it interferes with neurotransmitter synthesis. And so ammonification is very, very dangerous. And that's one of the effects essentially of liver failure is ammonification. So here's a table, again, shamelessly stolen from your book, of the essential amino acids. These are ones that you need to get from your diet. These are ones that you can make. So you don't need to get these from your diet. These you need to get from your diet. Histidine, of course, is one we can make ourselves. Children will need it. We don't. So histidine would be over here for adults. The rest of these, you can't make them. You need to get them from your diet. No, not today. For another chapter, you will. All right. Are there any questions from any or all of this energy production, anything like that? Yes, Kelsey.
What did you say that the desaturation, where were they derived from and what they did?
The desaturases, because when the fatty acids are made, they're made of saturated fatty acids. To make unsaturated fatty acids, they go through this machinery in the smoothie R called a desaturase. The desaturase consists of a complex of about six proteins. No, that's elongase. Desaturase is a complex of 4 proteins, and they will take fatty acids and they'll make certain proportions of unsaturated fatty acids. And there are some fatty acids that we cannot make that we have to have in our diets. There's 2 of them. Alpha-linoleic acid and alpha-linolenic acid are the 2 we need from our diets. The rest of them we can make. Very good. If there are no more questions, let's talk about transport mechanisms, because this will get us into action potentials and the nervous system. Okay, this is going to give me trouble. All right, here we go. Now, let's say that Nana over here decided he wanted to play a really dirty trick on everybody. So he bought a nice block of Lindbergh cheese. I don't know if any of you have had the misfortune of being around Lindbergh cheese, but Lindbergh cheese stinks. So let's say he put it in a Tupperware and he opened it and he put it right here. Now, after a while, Evan is going to start saying, man, who's got a problem in here? And then pretty soon Bracken's going to say, oh, Evan, you're right. And then Bethany's going to start saying, oh, goodness, I'm getting sick. And then pretty soon by the end, Jamie and the gang back there will be saying, oh, good gracious, open a window. It's terrible. That's an example of diffusion. So the volatiles from the Lindbergh cheese go from an area of high concentration to an area of low concentration. That's diffusion. And this is the same thing. If you have a gas stove, methane or propane is not something you can smell. There are indicators that are put in that gas that you can smell. And if somebody leaves the gas on, or if you have a small child who likes to play with knobs, you can get the ones now that you push and do that. That way the kid turns it, nothing happens. Hey, hon, what's going on? Oh yeah, somebody played with that. Oh, I forgot to turn that off. And that way you keep from blowing the house up. So that's an example of diffusion. If you get diffusion across a membrane, that's not diffusion anymore, and that's osmosis. That's osmosis. So osmosis very simply is diffusion across a membrane. Membranes are semi-permeable. Small nonpolar molecules can pass through membranes. Very small polar molecules like water can pass through membranes. And some membranes, if they have a lot of glycoprotein on the outside, like we're going to see in several tissues, they're essentially impermeable to water. You need to have special channels called aquaporins for water to get into cells. Gases can also diffuse through membranes pretty readily. Polar and nonpolar gases will diffuse at different rates. Nonpolar gases will diffuse faster than polar gases, but gases, be they polar and nonpolar, they can get through membranes usually pretty easily. So biological membranes are semi-permeable. They will prevent the passage of most molecules. That includes ions, that includes sugars, that includes amino acids, that includes fatty acids, that includes lots of things. So it says in red there, know this. So put a star by it, take your highlighter out and highlight it. Make sure you know that. So here we have an example essentially of something moving from an area of high concentration to an area of low concentration. When the concentration across that space is equal, molecules are still moving, but you don't have any net movement. You don't have any net movement. And this is actually very important for cells because cells will have things move through the membrane, and that is an example of osmosis. Gases moving across membranes are also an example of osmosis, but this special example is usually called gas exchange. And osmosis occurs in response to concentration gradients. So, for example, if we take cells, let's say you take red blood cells, and you put them in a solution of 3 molar sucrose. The water concentration inside the cell is higher than it is outside the cell. Water, therefore, is going to move from the inside of the cell to the outside of the cell, and the cells are going to shrivel up. Once the water concentration has been equalized between those two environments, inside the cell, outside the cell, will water still move across the cell? Yes, but there's no net movement of water leaving the cell. For every molecule that leaves the cell, another molecule will come in. So while at first you get a lot of movement outside the cell, once you get to that equilibrium, like we saw here, you don't have any net movement. So this describes movement of solutes, solvents, and also gases. And I don't think this works anymore because I've changed. Yep, no, that doesn't work. So anyway, let's brainstorm about the things that regulate the rate of osmosis, the rate of diffusion across the membrane. Now, the big one is going to be concentration difference. Concentration difference. Where you have concentration drift differences, those will drive movement of molecules across the membrane, either into the cell or from the cell. That's probably your biggest driver, is concentration disparity. Permeability of the membrane, that will affect the rate of movement. Temperature of the solution higher temperature favors higher rates of diffusion because the molecules are moving faster. The more molecular movement you have, the greater the rate of diffusion. And then a biggie that's used a lot in your body, surface area. Surface area means you have more area where molecules can penetrate. And so surface area is important too. So concentration disparity, permeability of the membrane, temperature, and surface of the membrane. Cells, as it turns out, can vary their permeability to certain molecules. So for example, a resting neuron has a membrane that's 20 times more permeable to potassium than it is to sodium. That means potassium will diffuse into the cell much more rapidly than sodium. When that neuron becomes activated, now its permeability to sodium and potassium is going to differ pretty greatly. So cells can actually regulate rates of osmosis by changing their permeability. They do this by opening ion channels. That's significant for neurons and other neuron-like cells as well. So you can change permeability by, you affect osmosis by, there it is, changing permeability of the membrane, that's what neurons do, or by changing your surface area, like the way kidneys and intestinal cells do. So for osmosis to occur, the membrane in question has to be selectively permeable. The membrane has to be permeable to the solvent, but it has to be relatively impermeable to the solute. The disparity of concentration between the two sides of the membrane, that's what's going to drive the diffusion, the osmosis. So let's use a simple illustration. So let's say we have a 13×9 casserole dish. Let's take a membrane, let's attach it to either side of the casserole dish. On one side, we're going to put a solution that is 100 milliliters of a solution in which 180 grams of glucose has been dissolved in 1 liter. On the other side of the membrane, we're going to add 100 milliliters of a solution with 360 grams of glucose has been dissolved into 1 liter. So we have two solutions. One has a lot more glucose dissolved in it than the other. There's twice as much glucose, in fact, dissolved in the other. This one, therefore, has less water than this one. Now, if we put those two solutions on either side of a membrane, we're going to get osmosis. We're going to get movement of water. Water will move from this side, where it's relatively high, to this side, where it's relatively low. So here, 180, 360, water is now going to move. Therefore, the volume of this side will get higher. The volume of this side will get lower because you have net movement of water from the 180 to 360. At equilibrium, both sides then will be about 270 grams per liter concentration of glucose. That's due to the movement of the water. One becomes more concentrated, the other becomes less concentrated. Let's say we wanted to prevent water movement in that situation. So we exert a force on the 360 glucose per liter side. We exert a force that says water, stay out. That force that we would need to exert in order to prevent osmosis from occurring is called the osmotic pressure. The osmotic pressure. That's the force that would prevent the change in volume. The force that prevents osmosis from occurring from one side to the other. That's the osmotic pressure. And so solutions are said to have an osmotic pressure according to how strongly it pulls fluid from another solution. So osmotic pressure is a, no, I don't need to have the lights turned off now. There, how's that? Now you guys won't fall asleep now.
There you go, now the other two, now the other two.
This one or this one? This one or this one? That one? Okay. All right. Is some of you back there starting to nod off? And Maddie back there, I'm wondering about her sometimes. She thinks she should bring her pillow to class sometimes, but you're okay? All right, you're okay. So, Maddie, got my eye on you. No sleeping, no sleeping. I might have to start bringing you chocolate or something to wake you up. Oh, that's a motivation. Okay, fine. I'll bring a pin cushion. There, how's that? Okay, so it's you refer to solutions as having high or low osmotic pressures. And that has to do with their tendency to draw water from other solutions. That's what the term means when it's applied to a solution. So pure water has an osmotic pressure of zilch. There are no solutes in it. No, gosh, no, especially Spring Harbor tap water.
Okay, well, that was my question.
Yeah, DI water would be relatively pure water. Yeah, water pipes. Our water's not exactly Calistoga, if you know what I mean. Yeah. When this building was built, no water treatment was put in the building. And apparently putting water treatment in would be quite expensive. So when you guys fill up your stuff at the water dispenser down there, just think of that every time. I'd fill it up in another building.
Well, that one has the filter.
That one?
Yeah, the water fountain doesn't have the little filter.
No. No,
Oh, there's no filter in
Yes,
there?
it does.
there's no filter.
Is that why?
Yes, it
is
does.
that
It
why
has
it
the
comes out
little
slower?
filter.
I asked the people who installed it if they put a filter and they said no.
The water in here is better than the water in Foley. If you taste the water in Foley, it tastes like you're drinking blood.
There, that has a treatment. You can go actually to the maintenance closet in there. There's a water treatment center there. They replace the tanks every month. We don't have a water treatment center in this building. So, all right. Ahem, ahem, ahem. Getting back to the subject at hand.
The subject at hand is the water. It's terrible.
Gotcha. Do you need a moment?
Yes.
Okay, there's your moment. Now we're returning. All right. Solute concentration is measured using two different measurements, molarity and molality. Molarity you're probably familiar with from chemistry. Molality you might not be. Molality is really important when it comes to physiology. In fact, Katya, when you do IVs as a nurse, a lot of your IVs will, the concentration on them will be in molality. So pay attention, you need to know this. Right, so molarity, of course, is moles of something per liter of water. And how much is a mole? Well, a mole is a creature that digs through, sand and gets you. No, a mole is an Avogadro's number, 6 times 10, 6.02, 6.023, okay, 6, let's just say 6. 6 times 10 to the 23rd number of molecules. If you have that many molecules, that's a mole. If you have twice that, it's 2 moles. If you have 1.5 times that, it's 1.5 moles, so on and so forth. And the weight of that 1 mole of a substance is atomic weights. And moles are very useful if you're doing stoichiometry. And I used to always tell chemistry students, how should you dig into this problem, trying to hint them to go back to moles. And they never quite took the hint, but so molarity simply moles per liter, 1 mole per liter, that's 1 molar, and molar is designated as a capital M. And so a mole of glucose is 180 grams. You dissolve that in a liter of water, and you have a 1 molar solution of glucose. And that's essentially how that works. And, you know, Bob's your uncle, and there you are. Now, molality is a bird of a different feather. So molality refers to a mole of a substance dissolved in a kilogram of water. A kilogram of water. How much is a kilogram of water? 1,000 grams, 2.2 pounds. So you dissolve that in a kilogram of water, you get a 1 molal solution of water, of glucose in water. That is designated with a small m, small m. Now, molalities are additive. So you can have a total molality. Say you have 1 mole of glucose and then 1 mole of sodium chloride in your solution. You have a mole of glucose, you have a mole of sodium ions, and you have a mole of chloride ions. So that's 1 + 1 + 1. That's a 3 molal solution now. So the total molality of a solution is called the osmolality. The osmolality. And the osmolality tends to be abbreviated with usually OS or something like that. So you have a 1 mole solution of glucose, 1 mole solution of sodium chloride. In a kilogram of water, you can say one of those, but actually it's going to be one of these. That's actually 3. But I'm trying not to complicate it here in this case. But anyway, you get the point. So these two are additive. But if it's sucrose, essentially, sucrose doesn't ionize, so it's just your osmolality is 2. So these are additive. Now, the main unit of molality in physiology is milliosmoles. Milliosmoles. So in this case, you'll use a 0.3 molal solution of glucose. You have a 0.3 moles of glucose. So you take 0.3 and multiply it by 180. You dissolve that in a kilogram of water. That gives you a 0.3 molal solution of glucose. That's 0.3 milliosmoles. And that is designated as a little m with an OSM like that. That's how you designate milliosmoles. Now, 300 milliosmoles is the same concentration as blood. And so if any of you heard of a solution, gotcha, I'm sure you've heard of this, D5W. D5W is 5% glucose and water. 5% glucose and water, D5W, is 300 milliosmoles. And that's a very common, well, you've heard of it now. That is a 300 milliosmol glucose solution. And if any of you have had a procedure, you're usually supposed to be NPO before the procedure. NPO means nil per os, nothing by mouth. NPO. If you're NPO, nothing to eat or drink, usually.
Well, I was right there. See?
You were on the right track. Give yourself credit. Give yourself credit. So I'm going to make you ahead of the game when you get to nursing school.
I already have a biology degree.
Right. So you're welcome. So you're NPO and usually you're thirsty and you're a little bit hungry. So they're usually going to start an IV. And that IV will usually be D5W. Or it may be something called NS. NS stands for normal saline. Normal saline is a 0.5 molal solution of sodium chloride. And now you have 0.5 molal of sodium ions, 0.5 molal of chloride ions, they ionize, so you have a 300 milliosmol solution. That's used for IVs as well. So let's say Maddie back there, yes, I'm picking on you, Maddie, pay attention. She's on the track team. I got that right? Okay, good. Sometimes I mix track and soccer. I don't know why, I just do. So if I say soccer, just throw something at me and say track. What do you run, by the way, in track? Your distance, so indoor, they don't do 10,000, they do 8, 4, 5, 6. They go up to 5, but outdoor, you'll do 10. Oh, okay. 10,000 meters looks to me like you should bring something to read. Now, do you count the laps, or do you have someone count the laps for you? Right, because I'd lose track. It's just, plus I'd really want to have something to read. It's just, how do you do that and not get terribly bored? That's just like, okay, give me something to read, please. Okay, let's say Maddie out there to train for her distance. Let's say Maddie gets up on a Saturday, puts on her running shoes, but it's cold out there, so she dresses in her parka and everything. And she goes out to the trail, which is full of snow right now. I know, because I was out there this morning with Chuck White. And so she goes up to Concord and she gets done with the trail. She turns, then goes towards Pulaski on Main Street. And she runs past Bethany's house. She waves, hi, Bethany. And hi, Dawn. Hi, okay. And she runs past Bethany's house and she gets to Pulaski, but she's in this parka. What's going to start to happen in that parka? You start to sweat. She is going to start to get dehydrated. Pretty soon, her blood osmolality is going to go up. It's going to go way up. And that's going to affect her cerebrospinal fluid osmolality. And she's going to start running in circles and not know where she is. And then pretty soon, her gait's going to get funny. And then after a while, she's just going to pass out. Okay, so let's say Evan's going that direction just because Evan likes to go for a drive. And Evan finds her passed out on the side of the road. And she says, Mads, what's up? And Mad goes, oh. She sounds like Joe Biden during a press conference. And Evan says, doofus, you didn't take anything to drink. So he pulls out his Gatorade. Okay. Gatorade says, Mads, here, drink. And Mads goes, and she drinks. Okay. That Gatorade is going to replenish the liquid and the solutes that she left. And then Evan, because he's a good chap and he's got a girlfriend, so he knows how to treat a lady, gives her the Gatorade and says, drink, okay, take this with you. In fact, here's another one. Stick this, I don't know, in your waistband or something. And that way you'll have something to drink when you get home. And Maddie starts home and she gets all the way back, okay? This essentially, if she had to go to the hospital and they had to put an IV in her, they would put in either normal saline or D5W. And then Maddie would learn a lesson to never do that again without taking water with her. Okay, now that I picked on Maddie, I'll pick on somebody else next time. All right, so these solutions, D5W, normal saline, they're osmotic, isoosmotic to plasma. They have the same solute concentration as plasma. So when you get these IVs, those IVs essentially will replenish your liquids and your solutes in plasma. And some of you, I think, want to become athletic trainers. And athletic trainers, especially for aerobic sports that are done outdoor in the heat, you'll have IVs, and one of your jobs will be to put these in if people start on soccer fields and sometimes baseball too. I know this happens. People will need an IV after really, really hot baseball games or something like that. And the trainers essentially are trained to do that and what have you. And you'll get a solution that's isoosmotic to plasma. Now, the relative strength of osmotic concentrations, the differences between them and the tendency for one fluid to pull water from another, or for the tendency of a solution to pull water from cells. That tendency is referred to as tonicity. Tonicity. So tonicity will describe the effect of a solution on the water movement in cells. So if we use normal saline and we put your tissues in normal saline, do we get any net movement of liquid? No. No. And in that case, the solution is isotonic. Isotonic solutions cause no net movement of fluid. There is movement, but there's no net movement. And this is illustrated here with the different types of molalities of glucose or salt or what have you, or something like that. Now, red blood cells. If you put red blood cells in a solution that is isotonic, your red blood cells will stay as they should be. They'll stay nice dish cells. They don't get bigger, they don't get smaller. That's what happens if you put red blood cells in D5W or normal saline. If, however, you were to put those red blood cells in a solution that has a greater solute concentration than that of plasma, let's say instead of putting them in a 0.15 molal solution of salt, you put them in a 0.45 molal solution of salt. You're now going to get movement of water from the red blood cells into the environment. The red blood cells are going to shrink. That's called crenation. Those types of cells are called crenated cells. Such a solution is hypertonic. Hypertonic. It's hypertonic because the tonicity is above that of red blood cells, so it pulls water from the red blood cells. So it's hypertonic. Think of tonic as tendency to pull water. Yeah.
So like when people die in the ocean, the water is so salty, is it because like they drink the salt water? Like,
Yeah.
the ice,
And it pulls water from their cells. So this water that you have had to drink actually makes you more thirsty and more dehydrated. Now, a hypotonic solution would be one in which the tonicity is such that the cell will now pull water from the environment rather than the environment pulling water from the cell. So this is hypotonic. So now the cell pulls water from the environment. So this is an example of what would happen if you put, say, a red blood cell in distilled water. The cell will swell up enormously and it'll actually burst. And this is an old lab trick. When you're isolating white blood cells from water, you always get some red blood cells that contaminate it. You just take the pellet, you dump in DI water, shake it up. 1001, 1002, 1003, 1004, 5, 6, 7, 8, 9, 10. All your red blood cells are destroyed. And now you centrifuge it again and you have clean white blood cells. And that's an old trick from laboratory work to isolate white blood cells. Such a solution is a hypotonic solution. Hypotonic solution. Now, my dumb mnemonic for remembering this is that O, hypotonic, the cell, oh my, the cell gets really big. Looks like an O. So hypotonic, oh, Nelly, we're about ready to burst there. So that's my dumb way of remembering it. So if that helps you, then use it. If not, then come up with your own mnemonic. All right, so blood osmolality is very carefully controlled. And it is controlled by osmoreceptors that are found in the hypothalamus in the brain. Those receptors are going to constantly sense they're going to constantly survey the blood plasma, and they're going to try and determine, is the osmolality as it should be? If you are dehydrated, like Maddie, when she goes for that long run to Concord and then Pulaski without taking water with her, that is going to tell her that she has essentially solutes that are too high. So that's going to do two things. One, it's going to activate receptors at the back of her throat. It's going to make her thirsty. Secondly, it is going to cause the posterior lobe of the pituitary to secrete a peptide hormone called antidiuretic hormone, more popularly known as ADH. ADH will tell the kidney to take more water from the filtrate. So now you make less urine, and that urine will be very concentrated. ADH tells your kidney to spare water. Spare water. So you get increased thirst, so you get increased water intake, and you get increased water preservation by means of ADH production. Now, as you drink, your solute concentration now will go down as you put in more fluid volume. That will feedback inhibit upon the receptors in the hypothalamus. That decreases the thirst response, and it decreases ADH production. And now your body, see, this is an example of negative feedback. Your body goes back to homeostasis, as said here. All right, questions about that before we move on? I always get this question every year, and I'm sure some of you might be thinking of it. So I will go ahead and answer it. And the question usually goes something like this: which should I drink if I'm working out or on the pitch or something like that? Should I drink water or should I drink a sports drink? I always get asked that question. If you are exerting, your sweat contains water, but it also contains a lot of solutes. You need to replace those solutes. Those solutes are important for muscle contraction. I would drink a sports drink. I would not drink a sports drink if you're doing a light workout unless you're sweating buckets. So if you're on the treadmill and you're sprinting and you're just really, really dripping, then replacing solutes is probably important. If you're lifting and you're sweating a little bit, sports drinks are probably not a good idea. Also, you should not casually drink sports drinks. You only drink sports drinks because the sports drinks, I don't know if you've read the ingredients, they have a lot of salt in them. So drink those to replace when you've lost a lot. So Mads, after practice, you guys do the 200, the 400s several times. You probably sweat buckets doing that, even in this cold, probably. Yeah. Sports drink is probably the better way to replace your solutes. If you're just working out, say you're doing legs or something, or you're doing, I don't know what your workout routine is, so whatever you're doing, and you're just sweating a little bit, water. Okay. And just limit the amount of sports drinks. One, because they're expensive. Two, because you don't need that much salt all the time. You really don't. I have a friend in my Bible study. She constantly drinks Gatorade. One, that stuff is so sickly sweet. I like it. Two, you don't need that much sugar and salt. You just don't. So, yeah, anyway. We've had that conversation. She's chosen not to listen to me, which is fine. It's not the first person not to listen to me. I have lots of students who don't listen to me. All right, so passive diffusion. If a cell takes up something via passive diffusion, no energy input is necessary. The cell doesn't have to put in energy to getting that molecule. No energy output is required for passive diffusion. The cell doesn't need to use energy to get oxygen or something like that. You read me, right? You feel me, right? Yeah, okay. All right. So water, gases, other types of nonpolar things that can enter cells, steroid hormones, things like that, they charge right through the membrane. You don't need any energy for those things to get into the cell. Now, there's a type of diffusion that is mediated by membrane-embedded transporters. These membrane-embedded transporters are called facilitated diffusion transporters. They work on the basis of concentration differences. So theoretically, they can work in any direction. They can bring things into the cell, they can kick things out of the cell. So what do you use them for if you're a cell? You use them for molecules that you're going to bring into the cell and then metabolize very quickly. One of the main molecules that you're going to metabolize quickly is glucose. Glucose comes into the cell, lickety split, it is metabolized. So virtually you will always have more glucose outside the cell than you will inside the cell. So facilitated diffusion is saturatable. That's how you can tell the difference between passive diffusion and facilitated diffusion. Passive diffusion is not saturatable. Facilitated diffusion, because the transporter works like an enzyme, it's saturatable. So not many molecules, at least in our cells, are taken up by facilitated diffusion. The big one is glucose. And there are several facilitated diffusion transporters. We'll talk more about them. The big one that you'll hear more about later on in this course is a molecule called GLUT4, glucose transporter 4, GLUT4. It's a gluttony for has gluttony for glucose. Active transport. Now you need to put out energy to get this thing into the cell. That energy is either in the form of ATP, you hydrolyze it, or it's the energy stored in concentration gradients. Those are the two types of active transport. That's where we'll pick this up on Wednesday. Some of you will say tomorrow. Please don't be late. And there we are. Now, Luke can't come to lab tomorrow. I'm going to need someone to volunteer to help him make the lab up, because you really need 2 people to run the lab. So we'll try to see if my TA can do it, if Amanda can do it. If not, I'm going to ask for volunteer for someone to do it with Luke. So
Dane volunteers.
I can do it next week.
you can do it next week? Okay, then,
Thanks, Dave.
okay, Luke, Dane will do the lab with you. Okay? All right,
Awesome.
stay well.
Thank you.